Welcome ENET 130 at Bellingham Technical College. This is our semiconductors course, and the topic for today's lecture is PN junctions and diodes. So in our last lecture, our first lecture of the quarter, we went over semiconductor materials in general, how they differ from conductors and insulators, and most importantly, we went over electron probability distribution in atoms, how they change when atoms are bonded together, and we've started treating the energy of electrons in materials using energy diagrams. Introduced the concept of both electrons and holes as charge carriers in semiconductors, and looked at how the concentration and ease of movement of our charge carriers change when we dope a semiconductor to create an N or P-type material. So go ahead and fix in your mind an energy diagram again, like we did last time, thinking of a valence band full of electrons, a conduction band waiting to accept electrons that are promoted, and then having a hole created in the valence band. And remember also what happens to the Fermi level and the ease of promotion of holes or electrons when we dope. Now we're going to leapfrog from that point, did a little verbal summary of our chapter 1, and we're going to put those two materials together at an interface and look what happens both energetically and in terms of what charge carriers are available and what they can do. So when we put a P-type material and an N-type material together by diffusion in a single monolithic material, a single crystal, we get what's called a PN junction. And it's actually a little region of fixed charge in the material, like a little intrinsic capacitor that's made of the different charge carriers coming together. We're going to walk through in this lecture how we get that, and then think about the implications of a material that literally contains its own fixed charge would have in a circuit. So again, I'm using the annotated notes that are available in your Canvas page from our James Fiore semiconductor textbook, and we'll be highlighting in this lecture my notes and the diagrams that I think are particularly important to help you understand these concepts. Okay, so remembering what a P-type and an N-type material are, semiconductor materials are, let's take a little moment and think about how we would make a PN junction. This is not something that you can glue together or weld together. Silicon and other semiconductor materials tend to be ceramics. You don't make a junction by joining. You make a junction by taking a piece of undoped intrinsic silicon or other semiconductor material and diffusing your dopants in from two sides, and you let them meet in the middle. So this is one of the reasons why semiconductor fabrication is expensive, and it has to take place in very controlled facilities. So the good thing is the cost to do that is now fairly low, and they're small and plentiful. But this is not a simple type of operation. Luckily, it's well established, and so there's plenty of PN junction semiconductor materials available to us. So we'll be looking at what happens at that interface when the P-type dopants and the N-type dopants meet, and remembering what each one of them are. So let's fast forward. The PN junction, that's what we're going to make. So here's figure 2.1. Here's what a PN junction in a doped material looks like. We had the outer rectangle here represents our original piece of monolithic, and this is usually a single crystal of, we'll assume it's silicon, and in fact we'll assume all of our semiconducting materials are silicon unless otherwise specified. So this started out as a single crystal of silicon, and then somebody put this in a furnace and put a bunch of phosphorus, say, containing material over on this side that provides that pentavalent dopant that has that extra electron. So it's going to make a bunch of electron majority charge carriers, and it diffuses in over time and makes an N-type material. At the same time, in the same furnace, we have maybe some boron over on this side, and we let it diffuse into the intrinsic silicon semiconductor, and so we're populating this side, literally this side of the chunk of silicon, with a material that, remember, has only 3 electrons when silicon had 4, so it's effectively rich in holes. So it's going to create a hole-rich p-type material here. So you can think of that as having a lot of holes to carry charge, because empty spaces in the valence band carry charge. And so the negative signs in our pink N-type material represent those charge carriers that are supplied by the dopant, the majority charge carriers. So there's all kinds of electron charge carriers in the N, and there's all kinds of holes in the P given by the dopant, ready to carry charge. So what do you think happens when all of those extra electrons and extra holes meet up at the interface? They recombine, and a hole and electron come together, and they annihilate one another. So the pluses and the minuses add together, and you get 0 effectively in terms of a charge carrier. That's called recombination, and it eliminates 2 charge carriers, just like promotion of an electron to the conduction band created 2 because it left a hole behind. Well, now we're going to get rid of 2 when they combine. So now you can see on Mr. Fiore's diagram here, you've got some pluses and minuses with a circle around them within their respective materials. So this represents what's called the depletion zone, where our majority charge carriers from the 2 different flavors of dopants, our N and our P dopants, produced charge carriers that got together and canceled each other out. So this region that has the circled pluses and minuses is actually back to being just plain old intrinsic silicon, no dopants effectively. So the reason that these circle charges are really important is this is a region of what we call fixed charge, and it's literally a stationary charge separation that we didn't have to apply a voltage to get. It creates its own voltage effectively. And if you want to think about it, you can take a look at this and say, hey, we have some charges here that are all negative on one side, and there's a plane and all positive on the other. This ought to look a lot like a capacitor to you guys now. And in fact, if you think about a capacitor, it has its own voltage if you pile charge on it. The interface of a PN junction is a little tiny capacitor that has a fixed amount of charge, so it's got a fixed voltage associated with it in a circuit. And we are going to leverage that fact when we put these in circuits. Okay, let's think a little bit more about why we have this fixed charge though. So we had a whole bunch of majority electron charge carriers here, and they recombined, and so we got left with nothing. Why is it a plus instead of just a 0? The reason we're putting pluses here on the N side and minuses on the P side is because it's positive or negative relative to what that doped material wanted to have. So it's plus over here on the N side because we should have had a lot of electrons and now we have nothing. So it's a neutral charge seems positive relative to a material that wanted to have a negative charge because we doped it negative, and dopant. And likewise, we expected the p-type material expected to have an excess of holes, and now we took those away. So a neutral state seems negative from the viewpoint of a p-type material that wanted to be positive, and neutral intrinsic semiconductor material seems positive from the viewpoint of the N material that wanted to be negative because it's got a lot of excess electrons, majority charge carrier. So you can think about the circled charges as what was relative to the material it came from. But relative to some absolute standard, effectively this whole region in the circle we can think of as basically having no charge carriers. Wow. Or only the charge carriers we would get for an intrinsic semiconductor. So, if we heated the material up, there'd be more here, but nothing compared to what we would have in a doped material. So, if you think about relative conductivities, our N-type material is probably pretty conductive because we've got all these extra electrons from our dopant. Our P material is pretty darn conductive because we've got all these extra holes from our trivalent dopant. We don't have a lot of charge carriers here in the depletion zone, and in fact it's called the depletion zone for a reason, because it is depleted in charge carriers. So we've got a little bit of something that's going to act a lot like an electrical insulator sandwiched between two regions that have plenty of charge carriers and can act like a conductor. So this is an impediment to current flow. So we've got a sandwich now that's got a conductive end, kind of a much less conductive middle section, kind of like a filling in an Oreo, and then a fairly conductive side over on the P side. So this is one of the reasons why a diode, unless it's biased, unless we apply a voltage from the outside, isn't going to conduct the way a metal would. Okay. So the next thing that's important to look at is we're going to go, having looked at the physical construction of our PN junction, now we're going to go back to our energy hill. So we're going to look at that same exact PN junction, and we're going to look at how it would look from an electron and hole energy standpoint. It's all about the energy because that tells us about the voltage, and it's kind of going to tell us where this fixed voltage comes from a little better. So we're gonna look at the same kind of energy diagram. So we've got the energy of the electrons or holes here on the y-axis, and this is how much energy they have based on placement versus the nucleus in each other. We established that in our last section. And then this time the x-axis is distance, literal physical distance along the device. So the left side we're starting over in the P material, and in the middle is that depletion zone, and then over here on the right side we're into the N material, and then the negative lead going on the other side would be over here on the right. Okay, most important thing we're going to look at here is that Fermi level. So that was the energy at which we had 50% chance of encountering an electron, and electrons populate from the bottom. So now we're going to think of that Fermi level as kind of like a sea level or water leveling itself between two ponds. This is always going to be flat. Electrons are basically going to level themselves so that anywhere in the device we have equal probability. So remember, in an N-type material, this Fermi level was really close to the conduction band because we created that donor level in the middle of the forbidden zone, so we could promote electrons to the conduction band really easily. And we can see this over here. We can see this. The Fermi level now is pretty close to the conduction band, and that's because we've got those donor levels in there. And over here in the P-type material, it's closer to the valence band. It's not in the middle. Over here in the P material, it's closer to the valence band because you've got those acceptor levels where holes can jump down, because holes have to jump to go down into the valence band where they can conduct like crazy. So that's copacetic. That's what we went through last time. We've shifted where the charge carrier's average energy level is. And in the middle, if you wanted to measure the Fermi energy level right in the middle of this depletion zone, it's dead center, which is what we'd expect from an intrinsic semiconductor. So if the Fermi level has to stay constant, which we're just going to assume it does, something else has to shift because the material is continuous. There isn't a big break in it or it wouldn't work. So what has shifted are the actual energetic positions of our conduction and valence band, and that's shown here in the diagram. As we go from the P material to the N material, the energy of the valence band actually shifts down, and the same with the conduction band. So if we had a certain amount of energy in joules relative to some reference, the bottom to top of the valence band, those values in joules would be less over here in the N than the P. And there's a slope to the bands as you go literally, physically across the device from one side to the other. An energy slope with respect to distance. Now, this sounds a lot like a hill. I mean, if we were looking at a physical hill with respect to gravitational energy, potential energy with gravity, it would be a literal hill would be an elevation gradient, like a road going up a mountain. As you go across a certain distance, you go up or down and you change your potential energy. Well, that's exactly what's happening as we move from one side of this diode to the other. Excuse me. This is a PN junction, but the device it makes is called a diode, so I gave away the future there. So as we go from the N material to the P material, we actually have to climb an energy hill to get there. And this energy is per unit charge, so this is a voltage gradient. So we've created a voltage barrier, a voltage hill, that an electron moving through the conduction band or a hole moving through the valence band has to jump. So you can have all kinds of cool conductors, charge carriers, but they can't get over this hill. And remember, electrons need energy to climb the hill, holes need energy to descend the hill. So we got to provide energy for both flavors of charge carriers. So this is one of the features of a PN junction. It doesn't have a lot of charge carriers right within itself, but more importantly, the action of this fixed charge at the interface changes the position of our energy bands, and it creates a voltage gradient. So this is another way of looking at that fixed voltage of the interface. This is another way of looking at that voltage that would effectively be on what is kind of like a little capacitor at the interface, is this energy hill that we have to climb. And the size of the energy hill is very, very important in terms of what kind of applied voltage we need to get charge carriers to jump up or down over the hill. And so that'll be very important when we model PN junctions and turn them into devices that we use in circuits. And these become physical devices that we'll model the properties of and then use them in circuits, and then use them physically in circuits. Okay, so just some rules, some little notes here. Our depletion zone becomes the area where we have the energy hill. Electrons require voltage energy coming from outside of the device to climb the hill. Holes require energy in the form of applied voltage to descend the hill. If you don't have an applied voltage outside of the device, neither holes nor electrons can cross the depletion zone. So there's some rules that we're going to follow. Okay, we talked about applied voltage from outside the device. So let's apply some. Let's take our PN junction, our little doped material, which we're later going to call a diode. And so we've got our N-type material over here in the pink and our P-type material in the blue. And we're now going to apply some energy from outside in the form of an applied voltage. So we're going to put a current limiting resistor, which we're always going to put in semiconducting materials. Semiconducting materials don't like a lot of current unless they're specifically designed for it. So every circuit you see that has a semiconductor material in it, if it's got a voltage source, it's probably going to have a current limiting resistor. So that's why they're there. It's not just to make the schematic look complicated. It's serving a function to protect our nice delicate PN junction. Okay, so we got a voltage source. It's a DC source. So very important, the negative end of the voltage source is now connected to the N-type material, and the positive end is connected to the P-type material. And there is a dotted line in this schematic, not a solid line, and it's dotted for a reason, because this time it's showing not the direction of conventional current, but the direction of electron flow. And we're going to electron flow because we're talking about electron charge carriers in the N material. So it's really important that we understand things in terms of the proper flavor of charge carrier. Generally speaking, we're going to look at always conventional current, but when we're getting down into the nitty-gritty of a PN junction and different semiconductor charge carriers, we're going to use electrons or holes specifically. So let's walk our way around the circuit. We've got some electrons that come out of the negative end of the battery. They've got an energy that was imparted by the battery equal to whatever the value of the battery or the DC source is. So they're going to come in and they're going to enter the N-type material, and boy, they're the right flavor of charge carriers. We're going to create a negative voltage here on the side of the lead, and all these electrons don't want to be, they're negatively charged themselves, so they're kind of repelled. There's a lot of charge carriers here, so electrons are going to want to flow away from that negatively charged lead and towards the interface. So there, it's really easy to get them there, and so we got a little 1, 2, 3, 4, 5 notes over here of what's happening. So electrons are going to enter the N-type material from the battery negative terminal. This side's going to be negatively charged. Negative is repelled by negative, so the majority charge carrier is going to scoot across the N-type material towards the interface. And there should be very little ohmic drop because there's tons of N-type dopants in the N material, so it's not going to act like a resistor very much. We're not going to lose any voltage just getting across the bulk of the material. But once we hit the depletion zone here, those electrons are going to have to climb the hill. Now they're here. They're going to lose energy because they gotta heave themselves up this big hill that is caused by those bent energy bands or this fixed charge at the interface, and that's what's happening in region 3. We still have plenty of them coming across, but they're going to lose energy. They're going to be less zippy as they get across this. Very analogous to what happens to electrons flowing through a resistor. Their energy drops as they go through the resistor. So these electrons coming from the N material, originally from the battery, lose energy because they had to climb the hill. Okay, so something important happens to those electrons as they actually move through the depletion zone. They don't enter the p-type material and travel through it as electrons. So here's where we change versus the circuit components we've looked at before. In position 4, the electrons that are carrying energy into the p-type material, they're carrying charge actually. They've made it over the hill, and they don't proceed through the p-type material as electrons. They recombine with holes right here on the left side of the depletion zone. And there's plenty of holes to recombine with because there's positive charge coming out of the positive side of the battery and entering the p-type material from the back side, pushing all the positively charged holes up towards the interface. So here we're on the number 4 side of the left side of that depletion zone. You got a bunch of electrons that have scooted across the depletion zone from the N side, recombining with a bunch of holes that have scooted across from the P side, and we complete the circuit in the depletion zone. And so those holes, or you can think of it as completing at the dead center of the depletion zone, and each are accurate. The holes lost energy because they had to climb down the slope, had to climb down. The electrons lost energy because they had to climb up. So if this battery weren't here, neither could have made it up or down the hill, respectively. But the battery gave them enough energy to climb the hill, so we completed the circuit. But in so doing, we did drop voltage. So if we went around the circuit with reference to ground, if we put a ground up here in this corner between the voltage source and the resistor, we would show that we would go down a voltage equal to the battery source, negative V, and then we would come back up going across this one. So we would basically have lost some of what the source gave us. Okay, and this type of operation where we use an external source to push charges towards the PN junction and climb the hill is known as forward bias. And in this mode, because we're pushing the charges towards the interface and we're giving a voltage to let them climb that hill, the diode conducts very easily. And it just doesn't take a lot of energy to get in the terms of external voltage, to get those charges to jump the hill or to climb the hill, or climb down the hill in the case of the holes, and conduct. So the diode is going to conduct very easily, or the PN junction will conduct easily in this mode. So this is known as forward bias. Okay, obviously there is an opposite way, reverse bias, and there's not a picture to go with it, but you can just imagine the voltage source polarity in our schematic up here being reversed. What would happen if we flipped the battery and all of a sudden we applied a negative potential to the P side and a positive to the N? One thing you can imagine in that case is all of the positive charge carriers in the P are going to get attracted to the back lead that's now negative and pulled away from the interface. And the same with the negative. And in so doing, what we actually do is make this hill huge. It's huge and no charge can cross it. So we've pulled all the charge carriers away from the interface, we've steepened the hill, we've made it huge, and now the interface acts as an insulator. It acts literally as an open in the circuit until you apply enough voltage to actually break it down and change the electronic structure of the device, which, with the exception of Zener diodes, is not good. So you would have destroyed the device in that case. So that's what's known as reverse bias. When we pull the charge carriers away from the interface, steepen the hill, nothing can cross it. So as a result, forward bias, we can conduct. Reverse bias, we can't conduct, and therefore diodes only conduct in one direction. So a diode being, I'm now blurring terms, a PN junction actually creates its own device, and that's known as a diode. A diode is just a PN junction, and you can actually buy them. They're physical semiconducting devices, and they are the simplest one we'll work with. So a diode only conducts in one direction. It's like a one-way valve for current flow. Okay, so we can mathematically describe how that valve works in terms of some characteristics that we can look up about our diode or our PN junction, which is, again, what we're buying in a diode. And this is known as the Shockley equation or the diode equation. You'll hear that referenced in textbooks and other electronic studies. So here it is, our friend the exponent function, which if you took time constant studies in DC switching, you've seen this before. So this is the exponent function that goes with natural log. So if you've taken some mathematics, you're familiar with this. But it has a very characteristic shape. It's very steep. So a line would be below it in most cases as we scoot across the x-axis. So this is the current versus voltage relationship for a diode. So if I apply voltage in the form of V sub D, voltage across my diode, I'm going to get this much current out. And so the current that we can get through a diode is exponentially related to the forward voltage that we put across it. And so this will actually give us a plot of how much current we can expect a diode to give us for a given applied voltage and a given temperature and a given maximum current in reverse bias. And so I sub S is the amount of current that will flow backwards through the one-way valve, which isn't very much. It's orders of magnitude less than what we can get in the forward direction, hence the one-way. So I sub S is our it's called reverse saturation current, the current which would flow through the diode in reverse bias. This is a characteristic of the diode, the particular diode, so it'll vary by make, and it's listed in the manufacturer's spec. So that's our coefficient out front. Temperature, Q and N are characteristics of the diode or material constants, charge on an electron. And V sub D again is the voltage applied across the diode itself, not the source voltage, but the voltage drop across just the diode. And of course, this would be positive or negative depending on whether we've put it in reverse or forward bias. So a positive V sub D corresponds to forward bias. So what does this give us? Let's take a look at how much current we get through a diode. So here's the current that the diode will let us flow, or the current across the PN junction. And here's the voltage that we're applying, forward bias voltage, just like the circuit that we looked up at in figure 2.3. So if we apply no voltage, we've got that energy hill. Nothing's going to go across. And we apply a little more and a little more, and we're not seeing anything. It isn't until we get to a little over half a volt that the diode starts to let current through. And that's a very important number, because what that is the voltage hill. That's the height of the hill. So it's taken an application of a voltage that is equal to, and I'm going to scan back, equal to the height of this difference between this bottom end of the conduction band and up here, this energy hill. So we have to apply a voltage equal to this energy hill, and it's the same here. So before we'll get any conduction in the forward bias. Now, needless to say, we get nothing in the negative. But here's where we have finally given our charge carriers energy equal to the hill. Okay, but that just means they kind of just jumped the hill, and they don't have a lot more. So to get more current through the diode, we have to keep giving it more energy from the outside. And once we do, it just takes off. This line goes almost vertical. This is the exponential relationship. This is way beyond linear. So once we get over that energy hill and we give the diode this much voltage across itself in the forward direction, every little bit more that we give past about 0.7, we just get all kinds of current. And really the line goes almost vertical to the point where we no longer really have to add more voltage to get a lot of current. So it basically doesn't provide much resistance once we get past this point, but we must supply about 0.7 volts in the case of this particular device to really get to where that line is vertical. So that is how the diode acts in a circuit with respect to how much voltage is dropped across it. This is its current voltage relationship. So it's very different than a resistor, which is just voltage equals its own resistance times current flowing through. In this case, the current is going to be this exponential function of applied voltage, and only in the forward direction. So we can turn this into a straight line if we put it on a log-log plot, but that's less important than knowing where this point is. So let's look at the whole plot. Let's look at how this diode behaves in reverse and forward. So here's our applied voltage across the diode going from negative infinity to positive, so we can apply a negative voltage to it and put it in reverse bias. So if we apply enough voltage backwards in reverse bias across that diode, eventually we'll break it down. We'll kind of destroy it, and in which case it starts conducting like crazy. It forms a short. We have effectively exceeded the dielectric strength of the semiconductor material, just like we can fail a capacitor by exceeding the dielectric strength of the insulating material between plates. We don't want to do that unless it's a special device that's actually designed for it, and those are called Zehners. So if you're not using a Zener diode, you never want to do this. You will smell the smoke and see the blue sparks, and this is bad. You'll have ruined your device and maybe part of your circuit. So we don't want to get near there, and that's why maximum reverse voltage is an important point to look for in your specs. You're going to want to establish that when you're designing a circuit and make sure your diode never sees this. Okay, but if you haven't mistakenly applied that, the current that flows backwards through a diode is really tiny, and that's why you're seeing the purple line representing current really tiny. It's still going backwards through the diode, but there's very little. So we go to no bias applied. So now the diode is just sitting there, and there's no current going either way. Now we turn our power supply in the opposite direction. We start applying more and more and more forward bias, and we reach that knee that we described in our diode equation, and we get past the knee and the current just shoots up. So this is the full plot of current versus applied voltage over a diode. Forward bias operation here and reverse over here. So pretty much diode acts like an open here, and diode acts almost like something between a switch and a short over here. So we'll look at ways to describe this forward bias behavior in the next lecture. We'll use some simple components to describe this behavior in a circuit. But this is the whole behavior that you can get from that PN junction. So a little bit of practical circuit schematic symbols for diodes. They're a little triangle with a line, and the triangle points in the direction of conventional current flow. So you can think of this as having the p-type material here, which is called the anode because it's got positive charge, all those holes in the p-type material, and the n-type is the cathode. So current, if you're forward biased, current will flow from anode to cathode through the diode. In at the p side, you can think of it the conventional current as being positive, and it pushes all those holes towards the interface where they can climb down the hill, and we get conduction. And the little triangle may or may not be filled in. And in a real device, there'll be some kind of band or other indicator to say which end is the cathode. And so you can look at that and say that's the material that's going to be pointing in the direction of current flow. So it's the N material. So if you're looking at your circuit and you've got a direction of conventional current flow, you aim the banded end in the direction in which you're going to want to flow current. And you will have inserted the diode in forward bias in your circuit. Okay, that is it for this lecture. Next time we're going to dive into diode datasheet interpretation and look at some real benchmark values for things like reverse breakdown and saturation current, and we'll pick up ways to describe the diode behavior in a circuit when we're operating in this forward bias region, and ways we can model it. We'll look at our first semiconductor models, and we'll put them into a few circuits and see how they work.